Hey everybody, Mrs. Durasi here. Today we're going to be looking at interval notation. So interval notation is another way to write an inequality. So in this first example here, this is saying A, B. Sometimes people think, oh, that's like an ordered pair, like X, Y. But when we're talking about interval notation, this does not mean X and Y. This is saying that on a number line, we are starting with the number A, which is actually a variable, of course, and we're ending at this right here. So this is saying that all these values between A and B would be a solution to the inequality. And here's the inequality they're talking about. You're used to seeing this inequality without all this other stuff here. So this is saying that X is in between A and B. That's the way you're used to seeing it written. This is called set builder notation. When we add on these types of parentheses in this bar, this is just read as all x's such that x is greater than A and x is less than B. This is known as a conjunction, and it's also known as an and problem. So what it means is that in order to satisfy this, both of these things have to be true. X has to be less than B and X has to be greater than A. So all those values in there. If we're talking about starting at A, this open dot though, this means that we're not including that value of A. So on this problem, A and B were not included because they have the open dots. If they were included, we would have the closed dots. So see, this is saying on a number line, we're starting with the value of A, but it's not included because of the parentheses, and then we're going out to B, and we're closing that parentheses because B is included. So this is another and problem, also known as a conjunction. I'm going to write conjunction over here. Conjunctions are just and problems. It's a fancy way of saying that. Conjunction. And so this would be saying all the x's such that x is in between A and B. We're not including A, but we're getting really, really close to it. And we are including B because x can be less than or equal to B. And that's the way that would be written in interval notation. Here's another example where A is included and B is not included. See how x is allowed to be equal to A but not B. That's the way that would be written. Okay, so what about if A and B are both included? Well, then we use these brackets. These brackets are saying that the A and B values are included. So x is less than or equal to B and x is greater than or equal to A. And that just means all x is such that this happens. So all of these from here down to here are called conjunctions. And that's because they're all and problems. Both of the properties have to be true. What if I asked you for something where x has to be greater than 4 and x has to be less than, let's say 3. So both of these things have to be true. X has to be greater than 4 and the x value has to be less than 3. Think about that on a number line. We have 4, we'd have an open dot. We have 3, we'd have an open dot. We have to be greater than 4 and less than 3. Is that possible that that can happen? No. So this is going to have no solution. There's no solution to this problem because both of these can't be true. In order to be an and problem, it has to be this middle part that's shaded in order for it to be a conjunction and an and problem. So that problem, of course, no solution there. What about if we just want all the x's such that x is greater than A? Well, that would look like this on the number line. So it means we're starting with this value of A, and let's just change this. Let's make this like 3 to infinity rather than using A to infinity. So we're going to call this 3. So that's saying then that we're going to start at 3, but we're not including it. That's why we're using the parentheses. And we're going out forever. See how it's shaded on forever? When we go out as far as we possibly can, forever, 3, 4, 5, 6, 7, 8, a million, a billion, a trillion, a zillion, whatever, that means that we are getting larger and larger without bound, and so therefore we have to call that 3 to infinity. Infinity will never have a bracket because we can't be equal to infinity. We just get closer and closer. You've probably heard the phrase by Buzz Lightyear, to infinity and beyond. So since we can always go beyond, if you say the largest number you can think of, I can go beyond it just by adding 1 to it. So therefore, that's why we use parentheses always on the infinity. So let's look at another example. Let's change, this is saying all x's such that x is less than b. So here's the b, this is the less than side over to the left. So this is written as we're starting way down here to the left, as small as we can get, like negative 100, negative 1,000, negative 100,000. Those are called negative infinity because we keep going on and on and on. So we're starting down here at negative infinity and we're stopping up here at b. So that's negative infinity to b. And we could have any number, just like I changed this to 3 instead of a, just so you understand a and b can represent any number. Okay, and then the other situation we want to look at is what if we're talking about every number we can think of? Well, that's called all real numbers. Set builder notation is x such that x is an element of the real numbers. We're not going to use that. We're going to write it like this. If we're talking about all real numbers, that would be negative infinity to infinity is the way that's written, everything. Go back up here. What if I had x is greater than 4 or x is less than 3? Oops, less than. Think about that situation. So now I would be saying, here's 3, here's 4. Always put the smaller number first here, and also in the inequality. This is saying that x has to be less than 3. Actually, let me change it. That's not what I wanted. I want to do x has to be less than 4, or x has to be greater than 3. Well, if we're talking about that, here's 4. We're talking about all these values less than 4, or here's 3, all these values less than 3. Only one of these things has to be true. So if I say pick a number less than 4, you could say 3, 2, 1, 0, negative 1, negative 100, etc. Or I could say, or your number has to be greater than 3. Well, you can now say 3, 4, not 3 on that case, but you could say 3 on that case. And now you can say like 3.1, 4, 5, 7. Well, if I have the word or, this now becomes actually everything would be a solution to that. So therefore, that would be negative infinity to infinity if I had to simplify it. All right, let's go down here and solve some problems, and I think you'll see why this whole interval notation is helpful. So solving a problem like this, either this has to be true or that has to be true. I have 2 problems to solve in one, so I'm going to add 1 to both sides. I get 2x is less than negative 4. Dividing both sides by 2, I'm going to get x has to be less than negative 2. For this one, I just have to add 3. So that's going to be that x has to be greater than or equal to 7. So here's what our answer is going to be then. Let me show the add 3 here. So then our solution is going to be either the x's we're thinking of have to be less than negative 2, or they have to be greater than or equal to 7. Putting this on a number line will be helpful. Here's negative 2. It's not included, so I use the open dot, and I'm going to go left, because it's less than. All the values of x that are less than this. Here's 7. I'm allowed to be equal to it, so I'm going to use a closed dot. I want the x's that are larger than it, so that's down here. So then these, when I read this number line, and I always want to have the smaller number first, this is called negative infinity because it goes on forever in the negative direction. So in interval notation, writing the solution in interval notation is going to go negative infinity to negative 2. Another name for the word or is union. And then this is going to start back up as 7, including 7, and down to infinity. This is what the answer would be in interval notation. So now I could ask you, is 0 a solution? Well, is 0 going to meet this requirement or that requirement? No. So 0 is not a solution. Is 8 a solution? Yeah. See, it's in our shaded region, and it's in between 7 and infinity. So when you see union, it just means either this has to be true or this has to be true. When we have a situation like this, where instead of being in the middle of 2 values, it's in the outer part, this is actually called a disjunction. It's not important that you know that vocabulary, but that is what it's called. All right, so looking at the next problem, we want to solve this one for x. And in this problem, we actually have 3 parts to it. We've got this, we have the middle, and we have the right. So left, middle, right. We have to get x by itself. This is like an equal sign. You're just thinking of it as an equal sign. Less thans and greater thans, you just treat them like equal signs. To get x by itself, I'm going to add 5 here, add 5 here, add 5 here. Wherever there's an equal sign, just like here, I'm trying to get everything, the x's on one side of the equals and the numbers on the other. Negative 10 plus 5 is negative 5. Less than or equal to negative 2x less than 5. To get x by itself, I'm going to now have to divide by negative 2. What happens when we divide by a negative? We have to switch that inequality around, don't we? So I'm going to have to flip the inequalities as I'm writing this. A negative divided by a negative is a positive. I have to flip this. This is going to be x. I have to flip this inequality, and a positive divided by a negative is a negative. Now, watch when I go to graph this. My smaller number is negative 5 halves, isn't it? So I'm going to have to put that here. My larger number is positive 5 halves. This goes here. This is saying x has to be larger than negative 5 halves. That's this side. And, this is a conjunction, x must be less than or equal to 5 halves. That's going this way. So what we're saying then is that the x's have to be in between these two. This is a conjunction, and I don't like the way it's written. You should never have the larger value come first. It should always go smallest to largest. This is smaller. This should be written first. This should be written here. The x still goes in the middle. X has to be greater than negative 5 halves. So x has to be greater than negative 5 halves. X has to be less than or equal to 5 halves. These are exactly the same, but this one is good, whereas this one isn't as good. Because this doesn't make sense. We're saying it's not going in the correct order. So now look at it. X has to be larger than negative 5 halves. That's over here. And x has to be less than 5 halves. So we're talking about using an open dot here, a closed dot here, because this is equal, that's not, in between there. This is called inequality form. Is it a conjunction or a disjunction? It's a conjunction, isn't it? Because it's in between. It's an and problem. When we see in between here, we have two inequalities that have to be satisfied. This must be true and this must be true. So conjunctions are always going to be and it's going to be that middle part. Whereas disjunctions are going to be ors, and they're going to be the outside part. See that? Outside part, middle part for the and. Now, back to our main goal here. Solve the inequality, write the solution in interval notation. Interval notation is like all of these examples down here, okay? Over here, we had actually two problems to do. So we had to go negative infinity to our value, and then we had to pick it back up and go from this value to infinity. So we had to use two of these because it was a disjunction. But for this one, we go from left, what's the first value we use? Negative 5 halves, up to 5 halves. Anything that's in this interval, any value in that interval, is going to be a solution. Okay, we're going to do an absolute value inequality now. This is going to be a little bit more challenging. First of all, when we have an absolute value, anytime we have absolute value, it must be an and or an or. It has to be an and or an or problem. We're going to figure out which way it goes when we have less than. So let's suppose that we have the absolute value of x is equal to 2. What's absolute value mean? Make it positive, right? What answers would there be for this? What can we take the absolute value of and get 2? We get 2 answers, don't we? X could equal 2, but x could also equal negative 2, right? Both of those are solutions, okay? When we have an absolute value inequality, we should put in inequality, not equality. See, that's an equation for absolute value. When we have an inequality for absolute value, that's when we're going to have the and or the or. So let's figure it out. If I have absolute value of x less than or equal to 2, how does that end up being written? Is it an and or is it an or? Well, let's figure it out. If I think about a number line, here's the number 2. The absolute value of 2 is less than or equal to 2. That works. What about negative 2? The absolute value of negative 2 is less than or equal to 2. That works. Well, it has to be an and or an or problem when it's absolute value and it's less than or greater than. One of those, it has to be one of the two. Well, think about it. Is negative 3, what's the absolute value of negative 3? 3. Is 3 less than 2? No. That does not work. Let's test this region. Negative 1 would be in between these two. What's the absolute value of negative 1? 1. Is 1 less than 2? Yes. So that worked. Test some other numbers. What about 0? What's the absolute value of 0? 0. Is 0 less than 2? Yes. Everything in here works. What that tells us then, when we're in between like that, that's an and problem. This is going to turn into x must be less than or equal to 2, and the x must be greater than or equal to negative 2. Every absolute value that's less than gets set up like this. Look at it again. This 2 changed to negative 2. This is pointing this way, then we use what's here, and then this. That's the pattern. Opposite signs has to be greater than the opposite of that, and it has to be less than 2. All right. So now let's do the absolute value of x greater than or equal to 2. Let's make our number line. Well, we know 2, absolute value of 2 is 2. Is that greater than or equal to 2? Yeah, that works. What about negative 2? What's the absolute value of negative 2? 2 is 2 greater than or equal to 2? Yep, that works. What do you think it's going to be? Is it going to be the and, like this situation? Or is it going to be an or? Well, check it out. Negative 3. Let's check negative 3. What's the absolute value of negative 3? 3. Is 3 greater than or equal to 2? Yes. 3 worked. Would 4 work? Negative 4. Would negative 4 work? Would negative 5 work? Yes, they're all going to work. Okay. What about here? Negative 1. What's the absolute value of negative 1? 1. Is 1 greater than 2? No. That area is not going to work. What about 3? Absolute value of 3 is 3. Absolute value of 4 is 4. Those are all greater than 2. All of these are going to work. So therefore, anytime I have an absolute value and it's greater than, that's going to turn into an or problem. So therefore, this is going to turn into x is going to have to be less than or equal to negative 2, or x is going to have to be less than or equal to positive 2. Okay, let's put some fanciness around this. This ends up being and. This situation ends up being or. I tell you, when I first started teaching this, and I was thinking, like, how can I remember whether it's and or for absolute value inequalities? Look at this, guys. Less than, right? Think of less than instead of just less than. Think of less than. And this is greater than. Instead of thinking greater, think greater. So if I have absolute value and it's less than and less than, if it's absolute value and it's greater than, then greater than. And it gets set up like this. X has to be less than or equal to the opposite, or X has to be less than or equal to, that should be greater than, sorry, greater than or equal to 2. Okay? Sorry, greater than there. My lines keep going out. Okay. Here we go. Let's go to this problem. Look one more time at this pattern here. It's going to be less than the opposite of this, or it's going to be greater than that same number. We're talking about those outer parts. All right. Looking here. This is absolute value, and it's less than. Less than. Is it going to be the middle and kind of problem, or the outer or kind of problem? Less than. Let's back up here if you need to. Less than is going to be in between, isn't it? So I have to use the opposite of this, negative 10. I'm going to have to be less than 3x plus 1, less than 10. Look at that. That's exactly how we did on this one. Opposite, points the same direction, x, it's that middle part. This is the setup. That's the important part of it. Okay, so now we're going to solve it once we have it converted from this to the inequality we need. So we're going to subtract 1. We're going to divide by 3. All right, so now our whole goal is to be able to write this as an interval notation. So x has to be larger than this, not equal to it, and x has to be less than this, not equal to it. Both of those have to be true. So this is the region we're talking about right in here. All of those are solutions. So in interval notation, I start from the left. I go to my first value, parentheses. I keep going down to my next value. That would be the answer in interval notation. All right, before I can even decide whether I should set it up like this, see, there's two ways to set it up, either like this or like that. Before I make that decision, I have to get the absolute value by itself. I got to get rid of that 1 first. Get rid of the 1 first. So I'm going to subtract 1. So we get this. It's greater than. Is it going to be set up like this one was? Or is it going to be set up this way as the disjunction, as the or problem? It's greater than. It's going to be the or problem. So I take this to convert it from the absolute value into the inequality form. I'm going to have to do I'm going to have to do 2x plus 3 is less than or equal to negative 6, or 2x plus 3 is greater than positive 6. So when I set these up and I change this sign, I have to change that direction too, because we're talking about those outer parts. It's an or problem. Whatever's inside of here has to be outside of that distance of 6 away. So now I'm going to solve this. I'm going to subtract 3. X has to be less than or equal to negative 9 halves. Subtract 3. So this is an or problem. Okay, do the number line if you need to. Come over here and just do it real quick. Negative 9 halves, 3 halves. I have to be less than or equal to this. So that's this way. I have to be greater than or equal to this. It's an or problem. I should have the outer parts. On an or problem, I should have the outer parts, which I do. And so now I can write it in interval notation. Negative infinity to negative 9 halves, right? Negative infinity is all this down here, up to negative 9 halves. Union is the same thing as or. 3 halves to infinity. That's our final answer. Okay, guys, last thing we're going to talk about is domain and range and using interval notation on that. Domain is the x's that we use when we graph the function. What x's can we use when we graph the function? The range is the y's we can use when we graph the function. Domain and range. I need to think of what kind of function this is. F of x just means y. How do we graph y equals 3x minus 4? It's just a line, isn't it? So I'm going to go to negative 4, put a dot. I'm going to go up 3 over 1, up 3 over 1. Here's what this looks like. I look at this. This is the x-axis. This is different from the inequalities. Now I'm looking for the domain. The domain means the x's I can use. Well, these x's, this graph goes on forever. So these x's go way down there to the left. So the domain is going to be negative infinity, and then the x's it goes up and it goes way over in the x direction. So it's negative infinity to infinity. For the range, that's the y values that we use on this graph. Well, we have all these y values, and they go way down and they go way up. What do you think the range is? It's the same thing, isn't it? Negative infinity to infinity. I want to show you how you can graph this on your calculator too. I know some of you haven't used your calculator much. So if I want to graph this, I just go to 3, and I have to find the x. The x is right here. So 3x minus 4. And then I'm just going to hit, now to get a standard screen, we do a zoom standard screen 6. That's how I'm graphing it, zoom 6. Doesn't that look just like the line we just graphed? Remember, you can also use Desmos. Some people like to use Desmos to graph, but I want you to get used to using your calculator, but just to show you. There's the graph on Desmos. But try using your graphing calculator. All right, does everybody know this function? This function is y equals the absolute value of x minus 2 plus 1. F of x is just y. Do you guys know what an absolute value function should look like? It should just be a V shape, isn't it? It's a V shape. If you've forgotten that, you can go to Desmos and look at it. What does an absolute value function look like? Let's say you don't know how to use a graphing calculator yet. I want you to learn, but here's your other option. So I can go here, I can go to functions. Actually, I don't even need that. Here's absolute value, never mind. And I can just type it in. X minus 2 plus 1. There's the way it should look. But I want you to practice using your graphing calculator. I can't let you use Desmos on the test, so you got to get used to your graphing calculator. So how do we put that in? I'm going to go to y equals. There's no absolute value key on here. It's kind of tricky. What you have to do is go under math. So you go under math. When you go to math, well, first, let me remind you, you have to be at y equals first. So you're at y equals. You go to math, you go over to num, and right there's ABS is absolute value. And I'll keep reminding you of it. We're going to type in our x, oops, not that one. Our x right here, x minus 2, get out of the absolute value, arrow over, plus 1. Now I just did a zoom 6, so I don't have to keep doing it over and over. I can just hit graph now. And there's the way it looks. So we've got the absolute value of x minus 2 plus 1 was our function. What do you think this point is right here? It's 2, 1, isn't it? Let's do a little sketch of that graph. So that point right there, that vertex was 2, 1, and then it just went up like this. Think about the domain and the range. So the domain are the x's. X's go this way. This keeps going over to the left, all the way as far as you can imagine. This keeps going over to the right, as far as you can imagine. What is that domain? Yes, negative infinity to infinity. We can use anything. The range, that's the y values that this graph contains. So I go from the bottom and I go up. Here's the first point I use in the y direction. What is the y value right there? 1, right? So in interval notation, the range is going to be bracket 1, comma, and then it keeps going up and up and up all the way to blank and beyond infinity. And we always use a parenthesis around infinity. All right, guys, I'm telling you, this first day is a lot, I know, but I promise you it'll get easier, and it's going to seem fine by the time we have our test over all of this. So don't worry too much if that felt a little quick. It's okay. We'll get through it, and you're going to do great. All right, thanks for watching. Have a great day.